Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker, Chapter 12, Part 3. In this chapter, we're going to go over multiple linear regression, the overall F-test, and the partial F-test. All right, let's start with the overall F-test. All right, in the overall F-test, we're going to test if all of the predictors taken together are predictive or their slopes are equal to 0 versus at least one of those beta j's is not equal to 0. All right, so essentially we can create an Anova table that will help us get our results. And here is our Anova table. What we do is we have the source being due to regression, due to error, or total. We have K predictors in our model. So, we have K plus 1 predictors in our model. So the degrees of freedom due to regression should be K plus 1 minus 1, which is equal to K. The degrees of freedom overall, the total degrees of freedom should equal your sample size minus 1. And then your degrees of freedom for the error, they have to all add up, so you can get n minus k plus 1. So just as we want to double check, k plus n minus k plus 1, right? That is equal to n minus k minus 1 plus k, which is equal to n minus 1. So we've shown that those degrees of freedom do in fact add up. Okay, we have our sum of squares. We have our sum of squares due to regression right here. Those are our yi hats minus our y bar squareds. We have our sum of squares due to error. That's our observed minus the predicted values, yi minus yi hat I squared. Then we have our sum of squares total, which is each observation yi minus the y bars quantity squared. So we've shown in a previous video that the sum of squares due to regression, right, plus your sum of squares due to the error is equal to your sum of squares total, right? All right, we also have, this is sum of squares. We also have the mean squares. All right, the mean squares due to regression, you're going to take your SSR and divide it by your degrees of freedom. So that's SSR divided by K. That's going to equal your MSR. Then your MSE should be your SSE divided by the degrees of freedom related to that error term. So you get SSE divided by n minus k plus 1, and that will give you your MSE. To calculate your overall F statistic, you're going to take your MSR divided by your MSE. So that F statistic is going to follow an F distribution where the numerator degrees of freedom is going to be equal to the K, and the denominator degrees of freedom is going to be equal to n minus k plus 1. So essentially here, you can compare your test statistic to the F distribution. Distribution is going to vary in shape depending on the numbers of degrees of freedom that you have. So in this picture here, we have some examples of F distributions. For example, the gray represents an F distribution with the numerator degrees of freedom equaling 100 and the denominator degrees of freedom equal to 100. The green is where the numerator degrees of freedom is equal to 10 and the denominator degrees of freedom is equal to 1. So depending on your degrees of freedom, you might have something that looks a bit more right skewed, or you might have something that looks a bit more symmetric. It's all going to depend on the actual degrees of freedom. Okay, but in general, let's just draw out a skewed right distribution for our F distribution. Okay. And here, if we want, we could set up our rejection region, reject HO. And here we have our failed to reject HO. And we could put alpha area here, and we could get our critical value. All right. When we actually calculate our test statistic, it's either going to be beyond that critical value or not quite at that critical value, right? And we can actually calculate the p-value based on that particular F test statistic. So when we calculate the MSR divided by the MSE, we have two scenarios, right? Our test statistic could fall beyond the critical value, right? And this area here, that's going to be your p-value. In this case, our test statistic was beyond the critical value. Our p-value is going to be smaller than alpha, and we will reject HO. In another scenario, we could have our test statistic being smaller than the critical value. And all of this red area would be our p-value. Right? And in this case, the p-value is greater than alpha. So as we're used to, we could say, you know, if your p-value is less than alpha, we're going to reject HO, right? And we're going to end up saying that at least one of the beta J's does not equal 0. And similarly, if we're doing this in context of the problem, we can say these predictors taken together have statistically significant predictive value on the outcome variable. Right? If our p-value is greater than alpha, we're going to fail to reject HO. And if we fail to reject HO, we're going to say the predictors taken together do not have statistically significant predictive value on our outcome variable, which means that all of these individual slopes, we cannot say that they're different from 0. So there's not an overall relationship between our predictors and the outcome value. All right, if we want to calculate the p-value, you can do this using an F table if you would like, but you could also do this using R. Okay, so I'm going to have a future video on how to do it in R, but I'll also show you here. So to calculate that p-value, what you're going to need to do is you're going to use the function in R, lowercase pf, right? So that says find the probability under an F distribution for my particular test statistic. Let's call that F test statistic. And then we're going to say degrees of freedom 1 are equal to K, and degrees of freedom 2 are equal to n minus K plus 1. And then we're going to do lower dot tail equals false, right? And that is how you can calculate the p-value directly from R. Now, if you want, like I said, you're welcome to use the tables if you feel more comfortable with that, right? You can look up each of the degrees of freedom for the numerator and denominator. You can go find your test statistic, and then you can get the p-value associated with that test statistic. Okay, so here's an example. Suppose alpha is 0.05 and we have 30 people in our study. We have 5 predictor variables that we're looking at, and we're asking ourselves, do all of these predictors taken together have statistically significant predictive value for the outcome variable? So what I can do first is I can find the critical value. So in this case, when alpha is 0.05, and the degrees of freedom 1 is 5, and then degrees of freedom 2, n minus K plus 1. So 30 minus 6 gives us 24 degrees of freedom. Then our critical value would have been 2.62. Okay, now suppose we calculate the test statistic and we get the value of 3.5. So we can already see that this test statistic is beyond the critical value. But if we want to actually calculate the p-value, calculate the area under the curve that's greater than 3.5, we can use this code right here. And we can say, give me the probability under the F distribution of this test statistic where degrees of freedom 1 is K, degrees of freedom 2 is n minus K plus 1. and the lower tail equals false. So give me the upper tail. And we find that this p-value is 0.0162. Okay. In this case, 0.0162 is less than our predetermined alpha of 0.05. And we can say that we're going to reject HO, and the predictors taken together have statistically significant predictive value on the outcome. Now, as we change the degrees of freedom in both cases, so if we change the number of predictors of our overall F test, the second scenario where we change our sample size, okay, all of these values, the critical value, the test statistic, the p-value associated with the test statistic, all of these are going to change. So you have to do it each time for every problem you're working on. All right, we're going to do an example in the next video, but I hope you learned something about the overall F test today, and I look forward to seeing you in our next video.